Okay, so um, here is part two. I'm going to try to do 2A and 2B. Now, just for reference, the reason I did most of these videos again, I think I'm going to put an intro video, uh, was to kind of start a discussion um, about each of these questions, to kind of go over how I went over them, and hoping that most people would either comment, "Hey, no, I think you're wrong. That we should try this method," or "Hey, here's another method." Um, so over most of the exam, I believe looking back at it and going over, I think I explained everything and was mostly accurate. For this one, I'm still a little unsure, but you can question my reasoning. If anyone out there who knows, please let me know. Email me, or hopefully before Monday, before we have to turn this in. So, anyways, so part two of exam one, 2A, 2B. So a positively charged conducting sphere is held by a perfectly insulating rod, is placed in the cavity of a neutral conductor without touching it, shown here. So that's shown here. Here's the conducting sphere. It's in the cavity of this conductor. Oh, I forgot to draw. There are charges along here. And the number of charges matter. So 1, 2, 3, 4, 5, 6, 7, 8. And then it's positive. 1, 2, 3, 5, 6, 7, 8. So the charges are equal because this is a neutral conductor, so it has the same amount of protons as electrons. So now, in part two, the sphere makes contact with the inner surface of the cavity. And so what they want us to do is, if the conductor is in under electrostatic conditions, we need to draw the net charge on the conductor, or how the net charge of the conductor will be distributed. And so for this part here, how I would draw this is, well, once this touches, the ball is electron deficient. So things want to be where they have, they're in equilibrium, where they have positive and negative charges. So one of these negative charges will want to enter the ball. Therefore, we'll have this. So just one, because it has one extra proton. So the one will enter there. Now the rest of the negative charges, 1, 2, 3, 1, 2, 3, will still be surrounding there, and we'll have our positive charges still on the outside. So 1, 2, 3, 1, 2, 3, 8. So here, I believe, is how it will be arranged. If you think about it, the way I thought about this was, if you had a positive metal ball, and now you touch it to something neutral, well, electrons will want to move onto this ball until this now. Electrons will want to move onto this ball until there's no net charge. Well, if that happens, now this is going to be electron deficient, and so this will become positive. And so same logic here. So now if we look at it, the conductor overall is positive, right? This ball is going to be neutral. And the overall charge, we have 1, 2, 3, 4, 5, 6, 7, 8. But here we have only 1, 2, 3, 4, 5, 6, 7 electrons. So therefore, overall, the conductor now is positive. So now, I think that's literally what you do for part A. Sorry for the shadow. It's nighttime now, so I gotta turn on the light, but whatever. So for part B, describe the direction of the electric field outside and within the cavity of the conductor. So I think it's talking about, so I have a couple, the electric field. So if we think about it, the electric field, let's say inside this conductor, if we drew a Gaussian surface, remember, the Gaussian surface is equal to charge enclosed over epsilon naught. Well, the charge enclosed inside the cavity is what? Well, it's a positive charge and a negative charge, so it's neutral. So overall, the electric field will be zero. It's going to have no direction inside the cavity. Now, directly outside of the cavity, we have all these negative charges. Well, remember, negative charges point the electric field points inward, or goes towards the electric charges. We know the positive charges are outside, and so we can even further say that the electric field starts on these positive charges and goes inwards towards the negative charges. And so what I think the question is asking, I'm not 100% sure if the question is asking about what about the electric field outside. If it is talking about outside of the conductor, then I would say that because it's overall positive, we know that the electric field is pointing outward, away from the conductor. Well, inside the conductor, the electric field is pointing, or I guess you can say outside this cavity, it's pointing inward towards the cavity, which is consistent with positive outside, we still have negative inside. And then inside the cavity, the electric field is zero. And we can do that by saying, doing a Gauss's law. I guess we could do the Gauss's law for the same thing here, right? Yeah, and so the charge is negative, meaning that the overall charge is negative, meaning that inside the electric field should be radially inward. Yeah, so I think that should be correct. If anyone has anything different, let me know. This is the only one that I wasn't 100% sure, but looking at it again, I'm feeling more confident. So yeah, let me know. Cool. Thanks, guys. Bye.